Hello, today we will be talking about horizontal control and how to do it using different methods, and the method for this presentation is the triangulation. So the triangulation today is our subject, and we will be talking about how to do that. So first we will give you an idea, the application areas, the requirements, the methods of solution, and the solution that we will be doing that in this course. So triangulation, it's again, as we said before, we are trying to find the horizontal coordinates of unknown points, and these unknown points, we know their coordinates, easting and northing precisely, and then give it to the people, the surveyors, whoever is using this utility, let's say, the horizontal control points for their works in surveying or other things. So the application area, it is large, to whole countries, like usually it is large areas or whole countries. Of course, we are based here, the measurements, they are all angles. We do not measure any distances. So for the measurements, we will do all the angle measurements inside the triangle. So we have, in triangulation, we have the basic shape is the triangle. So we have at the beginning, we measure the angles wherever we measure the angles, and we have, of course, all the measurements, they are just angles. Now the control needed, because we want to be from these angles, we have to be calculating the distances, and then from the distances we calculate the coordinates, easting and northing. So we have to start with a certain distance, although we do not measure any distances, but we have to have a measured distance, is what we call the baseline. So there is a baseline that we have to measure its length, and we have to start from a control station. For example, this is a control station. In this case, we have two control stations. If we have two control stations, then we do not have to measure the distance between them. We can find the distance between these two control stations using the difference in the coordinates. Also, we don't have to measure an azimuth. We can use the azimuth, find the azimuth from also the coordinates of these two control stations. But other than that, we can have just one control station, the azimuth of the first line, and the length of this base line. How do we do with the solutions? What do we mean by the solution? We mean that we want to find the easting and northing of unknown stations, and we have many methods. We have the solution of triangles. We'll check that in a bit, and we have the least square adjustment. Least square adjustment. We saw this method in many places in this course, and we want to mention again and again that the least square is the best results, will be drawn from this method, but it needs approximate or initial approximations for the unknown station. This is the main drawback of this method, but we will manage. We will be able to do that using certain tricks, certain crude or raw, any approximate calculations will do. We have other methods of doing that, but mainly we will see the two methods of the solution of the triangles and the least square adjustment. Again, the objective of triangulation is to provide a set of stations that we know their coordinates, and we'll be using this as a reference. So what are the objectives in general? These are just a couple of the objectives. It's not everything, but we use to establish the accurate control for plane and geodetic survey. So anybody who wants to do geodetic or plane survey, he can reference the coordinates that we produce using triangulation, and also we can use those points for photogrammetric surveys. So in photogrammetry, we need control points on the ground to reference our project, and that's why we will use these points for photogrammetry. Also, in case of geodetic surveys on a larger scale, we will use these points to determine the shape and size of the earth. This is in geodesy, and that's why we need these reference points. We measure latitudes, longitudes, and gravity. Also, we need to determine location of points for engineering works. Any kind of engineering works, we need to locate the points for construction and things like that. So, for example, if we are building apartments of long bridges, then we will be using those horizontal control points to locate the exact locations of the apartments or other components of a long bridge. We can fix the center line, terminal points, shafts for long tunnels, even if it's under the ground, over the ground. And if we have to do work over the control points, and for as we said, large scale areas, or then we will be doing this to detect crustal movements between one area and the other, between the continents. We can do that, and also we can find the direction of the movement of clouds. If you are monitoring clouds, if you have control points, horizontal control points on the ground, then we can determine, because we have easting and northing. So the movement of clouds, if you monitor them, you will see this cloud is going to the north, to the south, whatever. So a lot of applications, a lot of uses. We can put those control points, the horizontal control points, to work for that. And triangulation is one method of establishing this control. Now, how do we use triangulation? What is the principle? What is the basis for triangulation? Is that our triangulation, triangulation. So our base unit is a triangle, and in this triangle we know the triangle, it has 6 elements, 3 angles and 3 sides. Now, in the triangulation, we will be measuring angles. So all the angles of the triangle will be measured. So to be able to compute the other ones, like if we have 3 angles and 3 sides, to continue in our case to calculate these 2 sides, we have to have at least one side known. So this side, which we call the baseline, if we know it, we know the angles, we can use the sine rule or the law of sines and calculate the other 2. This is the general principle of a triangulation. Again, if we have in a triangle, if we have the azimuth of a certain line, which is the starting line, for example, and we have, of course, the angles inside the triangles, all these 3 angles, automatically from one azimuth here, we can, using this angle and this azimuth, we can calculate the azimuths of all other sides, or let's say other courses of that triangle. We use that in the course, in the surveying course, and we learned how to do that. It is just simple procedure. Now, we do not work with one triangle. Actually, we have series of triangles. Either they are joined together, like in this case, or overlapping triangles, like in this case. So we have different combinations, but at least we have always a baseline. We have to know it, or we have to measure it, and the remaining side as calculated, as we said, from one triangle to the other, because we are measuring the angles at the vertices. So look at this. We have measurements everywhere. We have angles, and we do the measurements. Note that here the overlapping, we don't have a station here. The stations, they are the vertices, they are here. So we measure all of these angles, and from the baseline, which is the only distance that we measure, and the angles here and there, we will be able to calculate the lengths of all of these lines, calculate the azimuths of these lines from the azimuth of the first line, and then we can calculate the latitudes and departures, and consequently, finally, we will be able to calculate the easting and northing of those points. The stations that we have here, we call them triangulation stations, as you can see here. So again, as we said, we call these stations as triangulation stations. We have the baseline, which is the only line that we measure, and all the angles that we have here, we measure all these angles. Now, what about these? These are the lines of the triangulation, and together with the triangulation stations, we form a triangulation network, and these triangulation lines, they tie together all the triangulation stations. The strength of the figure actually depends on the geometry of the locations of the points and the lines tying these points together. As with different surveyings, either horizontal control or vertical control, we always work in levels of the accuracy of the surveying. So it depends on the extent, the purpose, and the degree of accuracy. We always have in surveying, mostly we have 3 orders. Classifications based on the accuracy, it's 3 orders. First order, second order, and the third order or tertiary order. In the very beginning, we will be doing the first order points, and these usually far away from each other, kilometers, and then they will be densified by second order points, and then the second order points will be densified by the third order, and the third order points, we call it engineering order, like it's less accurate, still very accurate, but the engineering points or the level or the order of engineering, it is much less than the third order. So we have first, second order, and these points, they have certain, how do we differentiate between them, is that we have certain accuracy levels for the determinations, the measurements, and the calculations. First order triangulation is it is used to determine the shape and size of the Earth, for example. These are the points that represent or being around a vast area, a huge area for a whole country or even a continent or more than that. The second order points, they will be tied to the first order. As we said, it will be densified by a second order triangulation. If we want to work directly with the first order points, they are so far away from each other. So at the end application, we cannot find the first order. That's why we densify them, but we densify them by second order triangulation. And this works for a region that is a small country or a province, but still like it's a big area. But it's not a huge as a whole country, a big country or a continent or the whole world at least. So the third order triangulation, it is the triangulation that we densify the second order. So mostly what you will see if there is a surveyor wants to work, he will be working mostly on third order triangulation, unless he wants to be doing second order densification from first order, or third order densification from second order. But for any detailed engineering, we will be using the third order points, and we do detailed engineering and location surveys. These are the general specifications of the 3 types of the triangulation. Look at this, as we said, if we are working on a first order triangulation, baselines, here it will be from 8 to 12, and these empirical values, 8 to 12 kilometers, imagine this. So for the second order, 2 to 5 baseline, and the third order triangulation, 100 to 500 meters. The length of the sides. Now, the sides of the triangle, this is the baseline. But for the other sides of the triangles, it can be from 16 to 150 kilometers, 10 to 25 kilometers for the second order, and 2 to 10 kilometers in the third order. Of course, these are just a listing of the accuracy levels for the errors, for the spherical axis. Of course, this is a separate subject. Maximum closures, as you can see, for every order, as you go down with the order from first to third, we always have more permissibility to do the error. So the average triangular error here, it should be less than in the first order, less than 1 second, while 3 seconds for the second order and the 12 for the third order. So these are just a listing of the general specifications for each type of the triangulation systems in these orders. Now, the combination of triangles and the shape of the network. Actually, we have different what we call layouts, and these layouts, they are different from each other by the strength and the use and the suitability of using each figure in a certain area. So either we will use a simple triangle, or we can use a braced. See, here we have quadrilateral, for quadrilateral, 4 points and 4 sides, and then we brace them. Like these are the braces we tie them together, so it will be much more stable geometrically, of course. And or we can do a polygon. Is not a quadrilateral. Quadrilateral is 4 sides. Polygon can be 3 or more sides, and this is what we call central station. So the central station will add to the configuration. It will add strength, it will add diversity of the measurements, but all the time we will be measuring the coordinates, angles between the triangles, and will be used with the baseline and the initial control for calculating the easting and northing of all of these unknown points. Again and again and again, I will repeat that in triangulation, in the horizontal control, we are trying to find the easting and northing precisely of the unknown points to be used as a reference for further works. So when it comes to the layouts, we will be basing our layouts or our configurations into the triangle. So either we will have a single chain of triangles when we want to order them, or we have double chain of triangles, braced quadrilaterals, as we saw, center triangles and polygons, or a combination of the above systems. Of course, as we said, every configuration, every layout has its advantages and disadvantages. In the single chain of triangles, simply the triangles, they are joined together in a simple configuration. One triangle is joined to the other, and then another one and another one. This is a very suitable configuration when we are doing something like a valley between ridges. When we have a narrow strip of the terrain, then this is a perfect choice. Also, it is rapid and economic system. Why? Because it is simple to design and simple to measure in the field. This system is measured through one route, and that's why we do not, this is a disadvantage, this is why we do not have a method of checking the accuracy of the observations. And while we go with the measurements, we have to continue doing extra check baselines. Usually we have one baseline, but here we have to add more baselines as a check to control the excessive accumulation of the errors in the layout. And it is the least accurate method. So the simplicity of the configuration, simplicity of the layout is counteracted by a couple of disadvantages. The double chain of triangles, it has the same advantages and disadvantages, and for the usage is also used for a narrow strip of terrain. The braced quadrilaterals, they are two triangles that are overlapping. So this is a triangle overlapping with this triangle, overlapping with this triangle, and this what it gives it its strength in the geometry. So it is the strongest and this is the best arrangement of the triangle. And it means because of the geometry of these triangles, when they are overlapping, we can measure through different routes, and measuring through different routes will give us redundancy of the layout. And most of the triangulation systems, they use this layout arrangement. In the center triangles and polygons, as the name says, we have a triangle with a central station and another polygon with a central station and another polygon, quadrilateral, with a central station. This system, it can be used for big areas, and mostly it is expandable in all directions, so we can add here, and then we have one more center station, and we continue in all directions. We can do that, and we can do that, and continue expanding in all directions. Now, it is not as strong as the braced quadrilateral, but still it is strong, and because of so many instrument setups that we have to move the instrument and do the measurements of all these angles, it will have a slow work progress. If we have like a narrow valley between ridges and then another big area and things like that, and a construction site, so we might add traverse and then connect it to a single chain, and then we can do a centered triangles. So this is a combination of different layouts that we will be using to serve the area that we are trying to do the triangulation on. So regardless of the shape that we are using for that area, triangulation for the horizontal control, we can solve that problem. What does it mean, solve the problem? That means we want to find at the end the easting and northing of these control points, and we give these control points coordinates to the people to use as a reference. So the first method is the manual method, let's say, or the stepwise method, where we calculate something and we jump to the other, and this is what we call triangle solution method. When we solve, we will have multiple solutions from different routes. So if we go from this side to that side and that side, will give you a solution. If we change the route, it will give you another solution. In the least square solution method, as we knew, we will do the solution in one step, and we will not have multiple solution. On the contrary, we will have one, and this one solution, it is the best solution we can get from the provided measurements. I think going through an example is the best thing we do for the to understand the principles of the solutions in the triangle solution method or in the least square method. So we have two interconnected triangles in this example. So they are interconnected through the side. What is the required initial control? Usually we have the length. We need coordinates of this point, which is the control station. We need the azimuth of this line, and we need the length or the baseline AB. So we have azimuth, and we have the stations, and also we do a measurement of the base line. We do one single distance measurement. But in addition to that, for the field measurements, we have all the angles. Now, what are the unknowns? They are, as usual, the coordinates of all the unknowns. So this one is a control station, while the others, these are stations that we need to find their coordinates. Mainly, it is through the solution of the triangles using the sine law. So this is stepwise procedural method. First, as usual, as with the method for traversing, first thing, because we are measuring so many angles, we have to fix the misclosure of the angles. So adjust the observed angles. Then we will use the observed angles to calculate using the sine law. This one is measured, but we will calculate the lengths of these lines. Once we calculate the lines, we will take the azimuths of the lines, and then we will calculate the departures and delta E's and delta N's for every side. And once we calculate these, we will compute the station coordinates by adding, like we have for A, for the easting of point B equals the easting of point A plus the departure, which is the and of course we already calculated the departures and latitudes. So the departure, which is delta E between A and B, and the same thing, northing of point B equals easting of point A plus delta N, which is the departure, the latitude of line A, B. When we calculate B, we can use it to calculate C or calculate D. And this is what we are talking about when we are having different answers from different routes. So point C, it can be calculated from B and also from A. So we have to, they will not be the same. It's not always that they will be the same because of the random errors. Or point D, it can be calculated from point B or can be calculated from point C. And this is what we mean by different roots, different answers. So the order of the solution is very important. Here, when we want to calculate the lengths, we have, after we finish the angle adjustment, so we want to calculate, the order is very important. So we have, here we are adopting that we want to go for this line first, the second this line, 1, 2, 3, and 4. And how do we do that? It is through the law of sines. So, or the sine rule. After that, we will go and calculate the azimuths. We can calculate the azimuth actually before the lengths. They are not related. So either we calculate all the azimuths or we calculate all the angles, but or the lengths. So the length and the azimuth, because we will later on use the calculated length and the calculated azimuth in finding the latitude and departures. So we need LAB and we need the azimuth of the line. So the latitude, which is the NAB and delta N between A and B, and delta A departure between A and B. And this is what we will be doing for all of these lines. After that, we have to calculate the coordinates, and as we said, it is important that we take certain root and the coordinates xb equals xa plus delta ab. Actually here what we are using LAB, L means here the latitude and D is the departure. This is an example from another reference. In our notation in the surveying course, this is delta NAB, and the departure, this is delta E between A and B. So just the confusion. And we use LAB in our notation, it is the length between A and B. So when you read this example, maybe I would change the notation, but for now, this is what is in this example. At the end, we use delta E and delta N to calculate, as we explained before, to calculate the coordinates. Now, this is the advantages and the disadvantages. The same thing, but it is an advantage. Disadvantage is that when you have B calculated, or for example, C is calculated from two different roots, that means we can have two answers. This is an advantage in a way that we have one answer that will confirm the other. Yes, they will be different by a little bit, but if they are different by a huge amount, that means we have some kind of a blender or something wrong. But at the end, this is a disadvantage because we are after one value. Can we take these values from different roots and take an average? Of course not, because one will be dependent on the other. So we cannot just take an average of these different calculations. And how many different combinations are we going to do? So it's not an easy job. It is not the best thing to do. In the least square adjustment, as we knew before, we have a nonlinear relationship between the observations and the unknowns, and that's why when we want to solve using this, we have to prepare a data file, but the data file will need an initial approximations of the unknown stations. So what are the unknowns here? We have E of point B and N of point B. We do not have these values, so we have to come up with an initial values. The initial values can be done using manual methods or any other method based on the geometry. So we can use that, but anyways, we can at the end, without even calculations, if you have a clear geometry of the problem, you can predict it. You don't have to be very precise in doing the initial approximations, but at the end you have to come up with the coordinate approximations of the unknown stations. So what do we have here in the triangulations? We have to have coordinates of the first point. This should be coordinates of the first point, the length of a baseline, and we measure the azimuth of the line also, the length and the azimuth, and we have to have the measurements of all the angles. So here are the observations. They are all the angles. We have the control station coordinates. We have the initial approximations of the unknown stations, and we have the length of the baseline and the azimuth of the baseline. So now we want to prepare. It is actually the same for triangulation. It is the same sequence as in everything, like in trilateration, in resection, in intersection, in everything, triangulation, least squares, and even in the case of the traversing least squares, the order of the quantities in the data file, it is the same. So here we have, for this example, first of all, we have to prepare the data file. The basic thing is that we want a title, and this is the title line with the code of the problem. And then what do we have? The number of distances. How many distances did we measure? We measured only one distance, which is the baseline. So we have one distance. How many angles? We have 1, 2, 3, 4, 5, and 6 angles. So we have 6 angles here. How many azimuths? We have only the azimuth of the first line, A, B. So it is 1 azimuth. How many control stations do we have? It is point A. This is 1 control station. And how many total number of stations, including the control station? It is A, B, C, and D. So we have 4 stations in total. Now we provide the control station coordinates. After the control station coordinates, we provide the initial estimations of the other points. Then we have the length of the baseline, and because it's a measurement, it's a plus minus 0.05, so it is plus minus 5 centimeters, which is 0.05 meters. And we have the angles, 1, 2, 3, 4, 5, 6 angles, followed by the azimuth of line A to B, and it's 2105, 38.4, and this one is the 1 second plus minus 1 second is the precision of the measurements. After that, we will put it, of course, in a data file with the extension A out. We feed, as we did the least squares in the other cases, like when we are doing the least squares for the traverse, and then these are the results. Initial approximation. These are the control information. How many control stations, how many unknowns, how many everything, and then we have the initial approximation is reported, but also and the control point coordinates. This is the distance observations between point A and B. This is the baseline. So the distance is so and so, and here it is plus minus the standard deviation plus minus 5 centimeters. Angle observations, and every angle, this is how much is the measure of the angle, plus minus 15 seconds, the standard deviation. At the end, what do we have? We have the azimuth observation. This is the azimuth, and we have plus minus 1. We have 1 second. Can you see the accuracy, or let's say the precision, standard deviation of the measurements is 15 seconds, while here for the azimuth of the line it is 1 second, of course, because this is a control. This is a control, in a way it's a control information that we needed, so it must be measured very, very, very precisely. And this is what we do in the field, that the azimuth is always calculated in the best way we can, so it will have a small standard deviation compared for the regularly measured angles. These are the final results of the points. So A is the control station, it stays the same, and A, B, and C, and D, these are the easting and the northing of those points, plus the standard deviations that we have. the adjusted distance observation. This is we have an option here to adjust, to show the adjustment. It's always adjusted the observations, and as you can see, the distance that we measured, it has plus minus 0.0139. It is not. The residual is a 0. So here are the adjusted angles. Whatever we measure, the angles, they will be a little bit changed. The residuals are about 2.4, and the standard deviation of the adjusted is 3.39 seconds. Adjusted azimuth observation, the azimuth is still the same, because first we gave the azimuth with high precision, which with a small standard deviation. So this is another example. It's about braced quadrilateral. The braced quadrilateral, it has in the one that we have in our example here, it is 4 sides, because it's a quadrilateral, so 4 stations. One station is the control station, and these are the coordinates of that station. The baseline that we want to measure, it is 154. This is the length, and the azimuth of this line is 90 degrees. So this is the north, and this is 90 degrees, which is the azimuth of the line AD. These are the measures of the angles, and as we can see, BAC, it's from B to A to C. So it's this is how we measure the angles. When you want to measure this angle, which is at B, the first one at B, so we have to go from D to B, then back to point A. This is the angle here. And we continue. Observe all the angles, how they are measured. Most probably, we will be asking you for the training in the exam or something else to write the angles like that. So you need to be doing the angles in the correct way. So we have all the information. We have the initial approximations here. We did it using just simple calculations, and at the end we prepared the data file. The data file, we have one distance, which is the line AD, 154. We have 8 angles that we measure, and then we have one azimuth, and we have one control station, and we have total of 4 stations. Coordinates of the control station, the approximate values for the initial estimations of the other stations, the length of the line, or the baseline, it is AD, and this is the length, and this is plus minus 5 centimeters. These are the 5 angles that we measure, and with plus minus 15 seconds. This is the standard deviation for each measurement, and at the end, this is the azimuth, which is from A to D, and it is 90 degrees, 0 minutes, 0 seconds, and it is plus minus 1 second. We plug in this data file, we give it to the adjust program, and this is the result that we will get. So these are the control information, and these are control information for the adjust program. And the initial approximations, the control station coordinates, all the input is output again for us to have all the information in one file, which is the output file. The distance observation, and we have the angle observations, we have the azimuth observation. So all of these, they are listed, and at the end, this is the solution. If I ask you, where is the solution? This is the solution, which is the point B, point C, and their coordinates. Of course, we have also information about their standard deviations. And here, if you want to have an idea about how much these observations, how much they are adjusted, then you can look at these tables and report the adjusted observations, azimuths, and angles. So this is the end of this part about the triangulation, and as you saw, we are doing everything using least squares. Just simply come up with the initial estimates, prepare the data file, give it to the adjust program, and that's it.